Welcome to the NERI SimCenter Live Expert Tips. Today's presentation is provided by Kuanshi Zhong, who is a postdoctoral scholar at Stanford University and the lead developer of our earthquake engineering with uncertainty quantification application. And that's a mouthful, so we'll just refer to it as EE-UQ. Kuanshi's going to go over ground motion selection and scaling for nonlinear time history analysis using the EE-UQ application. And Kuanshi, thank you for being here, and I invite you to go ahead and begin.
Thank you, Matt. Thanks for the introduction, and thanks everyone for joining us today. And yeah, so today I just focus on the topic, the ground motion selection scaling and the nonlinear time history analysis in EE-UQ. And so let's get started now. So the long name for the EE-UQ is just the earthquake engineering with uncertainty quantification. And the idea is just that we want to predict the response of a building structure subjected to earthquake events, but also we want to quantify those uncertainties inherited from those ground motion uncertainties, structural modeling uncertainties, and also some academic editorial analysis uncertainty. And before diving into today's topic, maybe just provide some resource links here. So you can download our tool in our official website and look into our documentation and try out the example listed there. And also welcome your questions, feedback, and also feature requests in our SimCenter forum. And of course, register for a design safe account and the peer account to allow you get NJ account to get ground motion and running on the HPC on Stampede 2. Okay, with this said, just a few outlines today. So basically three parts here. The first one is the maybe just a briefly review of the role of nonlinear response time history, some basics of the ground motion and earthquake characteristics, and then example criteria that are used for selecting and scaling ground motions. And then the second part will be a demonstration of using EE-UQ. And today I want to share some interesting stuff with the example, looking into a warm bridge column and doing nonlinear analysis and evaluating the structural performance at Seattle. And you know, Seattle may have very complex earthquake scenarios from different seismic sources. And let's see what the ground motion characteristics can help us to inform much better design strategies. And last part, just open discussions here. And okay, so like a 101 type question, why nonlinear response time history analysis? There's a lot of benefits. Of course, directly estimating displacement demands, very important in performance-based seismic design and earthquake engineering. And this also helps us explicitly examine the elastic response history, especially including those cyclic deterioration and path-dependent damages like fatigue, fracture responses and their impacts on the structure safety. And look back to our practical engineering and the daily practices. There are a lot of places that actually implementing using the nonlinear time history to design new structures, design upgrades, retrofitting, and assess performance of either new or existing structures and calibrating design criteria, design codes as well. And on the right-hand side, just to show two examples. The right top just to show one example of our concrete member on the cyclic loads. You can see those degradation due to cracked concrete crashing and bar buckling and the fracture. Those things are really captured by our nonlinear response history analysis to inform our design strategy. And then on the left bottom, just one famous example in our tall building initiation, looking into performance-based design for seismic performance assessment of the 42 tall wall building in Los Angeles. And So first thing about the earthquake and the ground motions, ask ourselves, like doing ground motion time history analysis, what's the important intensity measures that can influence our structure responses. Of course, two domains, one in time domain. So you will have peak responses, PGA, PDB, and duration of the ground motion, the bracket type of duration or significant duration based on the energy intensity index, or some near fault features in your time trace to see those pause and fleeing step in velocity or displacement trace. Now, of course, recently very popular topic in the basin motions, you probably will see those long period of cyclic motion time history resulted from those reflection in your basin, deep basin there. Now, of course, in the other side, the frequency domain, seismologists more familiar with the Fourier spectra, structural engineers, perhaps on the other side, more familiar with the pseudo-spectral acceleration. And the idea of not only conditioning on one fundamental period, many codes and practices guidelines recommend to do the period range to select and the scaling ground motion for considering those higher mode effects and the period elongation due to the softening behavior after the structure damage. So of course, this are all the very important and influential ground motion characteristics. But if we look into the details, like those ground motion characteristics actually rooted back to the differences in the source mechanisms, wave propagation paths, and of course the local site response, local site properties as well. So for instance, on the right top, I just show one rupture plan that used for SCAC broadband platform simulation of the high-word faults. And it's actually a lot of things going on there. Magnitude fault type, that's the strike slip or reverse normal fault, and how the rupture occurs, where's the what's the rising time on each node there. Those things actually will propagate later to your surface level, get the surface ground motion, have different characteristics. And of course, at the right bottom, just a very famous example from the Mexico City earthquake in 1985, where people realized that the importance of those local site conditions and how they could influence the response spectra and amplify those the ground shaking at a specific range of the periods. And so typically, ground motion, both ground motion characteristics and the earthquake characteristics are carried out into the ground motion selection and scaling criteria, looking to in order to control them for a representative set of the ground motion to a specific site hazard. For instance, here I just list a few points from ASE 716. Ground motions should be selected from events with generally same tectonic region. For instance, if I look into San Francisco and specific tall building, then perhaps I would very focus on the strike slip earthquake itself, because it's representative of the Hayward and also the San Andreas faults events as well. And should be selected with generally consistent magnitudes and of course the site to the fault distance given the intensity level, and have similar response spectra shape to the target spectra as we described just a few minutes ago. In the nonlinear response analysis for MDOF systems, you have those higher mode effects and also the period elongation due to the damage. So appropriate period would help us to get better estimates of the real responses. And of course, that's following that point would be the period range guidelines that you need to fit in the target response spectra within that period list. And so with this said, I just maybe we can just jump into our EE-UQ too, and to see how we actually implement this. The ground motion selection and scaling. So in EE-UQ software, we have that event panel. I will later demo the two, so you can see them. But we have two functionalities there. One is the peer NJ record. So every time you open that, it will pump out a peer website login interface. So you need to have an account. If not, then maybe the link there will direct you to the peer website to register for account. And then we'll have the interface with the web servlets there to pass the information that for selection. And the second functionality is the local-based user-specified database. So you can provide a ground motion flight file that's including the records that you may want to look into and select and scaling them to fit the target spectra. And for the target spectra itself, we have actually three options here. First one is the USGS design spectra that's provides a link to the USGS web serve for ASE7 spectra there. And the second option is the USGS uniform header spectra that's actually also provide to the link to their web serve. The last one is the user-defined response spectra. So you can upload a CSV file that have two columns, one for the period, and the other one for the SA value, and then define target spectra to get into the ground motion selection and scaling. And so let me just jump into stop the presentation. We'll look into the user interface in our EE-UQ. So this is actually the EE-UQ user interface, and then on the you can actually, I want to mention, if you're it's the first time you look into this user interface, you probably will notice several important things. I will not dive into the details. You can look into our online document to find more descriptions. Key functionality is listed as RIP panels on the left-hand side here. UQ, uncertainty quantification, GI, general information, SIM, structure information model. Event is our EVT, is the ground motion panel here. FEM, application, EDP, engineering demand parameters, and the random variable. Lastly is the results. So here, under the event panel, here NJ records. Yeah, I'm actually using one user-specified ground motion, user-specified target response spectra here. Later, I will mention more detail about this response spectra. Then we have a couple of record selection criteria. You can specify range for magnitude, distance, via 30 duration here. And then once you log in and click select records here, you can see we have the scaling selection criteria and the weighting function. And those information actually sent back to the peer website, NJ website, to get the ground motion selection for you. And let's back to the presentation now. So the example I want to share with you today is that I want to share, try to evaluate bridge columns performance under the design earthquakes return period of 975 years at Seattle. And so the column itself, 24 feet tall, 48-inch section diameter, and the axial load ratio is designed to be 6%. And it has 18 number 11 grade 60 longitudinal bars. And the right figure just to show the OpenSys model that we built up. We use the fiber elements for spaced with 6 integration points, and build a zero length element at the bottom to capture those bound slip responses. And the steel O2 and the fatigue material are used to simulate the reinforcing steel responses. And the bottom 2 figures just shows the fatigue material, which follows the modified Coffin-Mason criteria to account the cycle and the strain amplitudes from random history strength history that the bar experienced under the earthquake, and then convert them to the damage index and to predict the bar fracture and the fracture potential. So basically, if the index exceeds 1.0, there will be a simulated fracture. And then the other values just to indicate how close the bar tends to get to that point, failure points. And then we try to focus on the global response, peak column drift ratio, but also the maximum fatigue damage index DI of individual bars. So because in this example, we just do 1D input. So I just want to look at the symmetric, look at half of those 18 bars and find out the worst bar there. And on the other side, the hazard part, Seattle is sort of a site that whose seismic hazard contributed by multiple earthquake scenarios. The nearby Seattle fault, strike slip fault, and then the far field, really far field Cascadia subduction earthquake hitting the in-slab and interface seismic sources into the structure. And then on the right figure here, just to show the deaggregation plots. So you can see those different earthquake scenarios will have different magnitude and distance to the structure at this 975 return period level. And the idea would be, you can just group them up and find out what's the median value or mean value, expected value for magnitude and distance. But then if instead of doing that, we can do a little bit more, like we can separate the three resources, three seismic source, and then try to select ground motion for individual source, and then analyze the structure and assess the performance, and then to see actually which scenarios most critical. Of course, the most critical is dependent on what structure performance or response matrix we're looking into. But the idea here would be we first quantify the differences in the seismic hazards using the CMS and the duration factor here. So in the bottom right, I just show two figures to contrast the CMS and the duration distribution for the three different seismic sources. And the biggest difference in the duration side, you can see the crustal earthquake relatively have shorter durations, 14 seconds in the media for the DS 5 to 95, 5 to 95 significant duration. And then on the other extreme end, the interface earthquake actually can produce really long duration ground motions. On the media, it would be going up to 96 seconds here. So the idea that in our EE-UQ2, we support that you can use user-described response spectra as the target spectra. So I use three different target spectra for each individual seismic source. And on the filter side, I have the filter for magnitude and distance, and for the duration, just to make sure that my selected ground motion has have the appropriate or very representative ground motion characteristics as we saw here in the deaggregation and the target responses spectra and duration distribution. And in the example, I just select 50 records for each scenario, and nonlinear response history analysis is conducted for each, submitted to the GNISIF, analyzed and conducted on the Stampede 2, and it took about like 15 minutes for the crustal earthquake case because the ground motion duration relatively short. And for the other two cases, it took about like 1 hour and 10 minutes for each, I guess. And that's wrong. The analysis, the 50 analysis actually were run in parallel. So that's the reason why it did not really bump the analysis time too much there. So with this said, I just want to go over the like the setup there. So for instance, here, I think the picture here, the page here I left over is the one that for the long duration, the subductional earthquake, the interface one. So you can see I actually put magnitude really up to 9.5, and then have the distance, far distance there, and try to constrain the duration. There's a point here that actually this going back to the NJ West database, which actually did not have those subduction zone earthquake yet, records yet. But in this example, just want to demonstrate the idea of implement this in EE-UQ. And then in the FEM, I just submit the, in the SIM, I just submit the my TICO file for OpenSys model of the bridge column itself. And then in the FEM, I provide a numeric solver to do the iterations and the error control there, tolerance as well. And for the EDP panel, we use the user defined. As we mentioned that we want to look into the global response, the drift ratio at the column tip, also those detailed damage index for individual bars. So here from 1 to 9, actually looking to the half of the cross section, just look half the bars there because of the symmetric feature. And I conducted 3 rounds before. I just retrieved those results from the design safe here. Oops, sorry. My design safe account credential just expired. Just logging back. And you can see here 3 analysis. I just want first to retrieve the press. So first quick one. So so this actually fetching the data and output files from design safe remotely and bring them, download them to the local, and first the results to create the table and the quick view figure in the result panel, which will come in a second. So we'll reach this page here, the REST panel, and it has first the table just to summarize the statistic of our EDPs, PID, peak drift ratio of the column. It's about 1.8% on average, and you can see the standard deviation as well. And I also have the acceleration, maximum acceleration at the column tip, and then the damage index here. And you can see actually under the crest earthquake is relatively very small damage index. Then on the second panel here, you can actually visualize the data, and you can do scatter plots and CDF, PDF, and you could also do some contrast plots, like looking into the drift ratio versus my fracture damage index here. Give me a scatter plot, x-axis, the damage index here now, drift in the y-axis. And of course, you just now you can, and also EE-UQ support you to just save the data to, oh, sorry, save the data. You can just put a name here, because I already downloaded the data before. I just do another 2 here. And then you can go into that saved directory and open this results class 2. And this gives you a CSV table of this results panel here. And you can, of course, do further post-processing steps with the data and to explore more. And I'm just doing example here. Just skip this few slides. So The first thing I did for the post-processing of this example is actually I plot the CDF of the peak lateral drift ratio of the column. And for three individual scenario. So you can see the crustal earthquake has a mean value of 1.8%, which actually we just looked into the table a few seconds ago. And then the in-slab earthquake actually reduces results to larger drift ratio, about 2%, while the interface one is relatively on the smaller side of the drift demand. And the second plot I've made is the maximum damage index in the column. So I found out which bar is the worst bar out of the 9, and then try to plot the CDF of the damage index there. So you can see this figure is slightly different than the left one. In this case, the crustal earthquake actually produce very small damage to the fatigue damage to the bar, while the in-slab and interface earthquake have much higher damage index here, 0.1, and that's on the median. But if you look into individual cases, it's, some of those bars under the design level is close to 0.7, and it's kind of like close to the fracture. And that's kind of like a condition in our design properties of this column. And then, of course, you can explore the modeling uncertainty in the design of our column, try different concrete materials, try different reinforcing steels. Then you probably will find more interesting stuff there. And then the second step I'm doing is just a plot what I did, similar to the figure we have in the EE-UQ user interface, but here to overlap the 3 cases, plot the maximum damage index fatigue potential against the peak drift ratio here. So you can see actually if I specify a specific drift ratio, the crustal earthquake scenario will have lowest fracture or fatigue damage potential, and the interface one will have the highest potential to see bar fracture failure there. And this actually going back to our duration distribution or duration targets of these three seismic sources. And crustal generally have lower, shorter duration, which do not pose those multiple or large number of cycles on our reinforcing steel. And while on that side, the interface one just accumulates those damage cycles by cycle and bring the structure to close to the damage state with a bar fracture. And so I guess that's the demo parts and the slides I want to share with you today. And let's dive into the last part of the discussion. And maybe I'm happy to answer questions and welcome to all the comments and future requests as well.
Great, thank you, Kuanshi. Really interesting and informative presentation. I think there are a couple of things that I want to cover or reiterate. One is that we interface with the Pacific Earthquake Engineering Research Center's NGA West 2 database for ground motion selection. Is that right?
Yes.
And those records are appropriate for shallow crustal faults. You used those records for the subduction zone scenario. And I know Pierre has done a lot of work on subduction zone ground motions as well. And just to reiterate your point about using the ground motion database available right now with the web service was chosen just simply because of out of convenience. Is that right?
Mm-hmm. Yes, just for demonstration. Yeah.
Okay. And then I guess I also wanted to point out that the results you showed first within EE-UQ covered the engineering demand parameters that are set up to be plotted within the tool, but you have access to all of the other results that you downloaded from Design Safe, or if you would run it locally on your machine, you would have had the output files that you had generated. to create other plots and figures and interrogate the data, the results outside of EE-UQ. Is that right?
Yes. So basically, you can get the structural responses, and then if you log in your Design Safe account, you can retrieve all the work there, including the ground motion records actually running the model, and then other configuration files about the analysis itself.
And you're providing parameters to the ground motion selection. And could you just recap the scaling process for how those records that do get selected, how they're scaled?
Yeah, so the ground motion scaling is done in the by the here NG West website too, and the scaling part is designed to minimize the mean standard error here as our selection. Basically, it will go into the period points as we define here, and then try to calculate the error between our media target spectra versus our media response spectra of our selected records, and minimize the error there. And of course, you can provide weights if you specifically interested in a specific period range, or directly specify the period range there.
Fantastic. Kuanshi, thank you very much for this demonstration. I want to encourage those that are watching online to check the SimCenter website for additional upcoming live expert tips with the NERI SimCenter. The SimCenter is funded under the National Science Foundation Award 2131111, and those opinions and views of the presenter do not necessarily reflect those of the National Science Foundation. Kuanshi is showing the upcoming live expert tips for the remainder of this calendar year, and we hope you'll register for those. You can find links on our website that's here at the bottom of the page. So once again, Kuanshi, thank you very much.